Hello everyone, welcome back to Spectrum classes. This is my next video in continuation with the term symbols. And here in this video, I am going to discuss the term symbols for transition metal ions in their complexes. So here, this many of the complexes which we are going to discuss here in this video and some more tetrahedral complexes which we are going to discuss in the second video because of the length of the video. Here you see all are octahedral. 6 ligands are attached to the central metal ion. So let's start with the video. First, I will take two examples of iron. Here we are having FeF6 3 minus, and here we are having FeCN6 3 minus. So these two compounds are octahedral and they are in same oxidation state. The only difference is of the ligand. So first we are going to discuss the effect of the ligands, and later on we are going to discuss the effect of the oxidation state. Here in FeH2O whole 6 2 plus. So here iron is in second oxidation state and here iron is in 3 oxidation state. So let's start with the video. Here I just selected this FeF6 3 minus and FeCN6 3 minus. So how if we are having this type of complexes given to calculate the term symbols, so we have to follow simple 5 steps. So the step number 1 is calculate the oxidation state of the central metal atom. So here what is the central metal atom? Iron is the central metal atom and fluorine is the ligand. We are going to calculate the oxidation state for this iron. So let this be the X, or suppose this is having oxidation state X in the equation, plus multiply with the subscript which is 6 over here multiplied by the charge on the ligand. So fluoride is having -1 charge and overall charge on this species, this complex ion, is -3. So this is equal to -3. Now on solving this equation, we are getting X is equal to 3. So this is the first simple step here. And you can also calculate the oxidation state of iron in this complex in the same manner. So here we are having iron is having, suppose, X oxidation state plus multiplied by 6 into Cn is again having -1 charge. So -1 is equal to -3. And here again we are having +3 oxidation state for this iron atom. Now the step number 2, we have to write the electronic configuration. Electronic configuration of iron in the neutral state or zero oxidation state, and this is the electronic configuration for iron in the zero oxidation state. So the simplest way to write this is 4s2 and this 6 is directly going to the 3d orbital. So 3d6 4s2. In the 3 oxidation state, we have to remove 3 electrons from this. So 2 electrons from here, from this 4s, and 1 electron from this d orbital. So after removing 3 electrons, we are having 3d5 and 4s0. So this is having this type of electronic configuration. In case of coordination compounds, it is not the case. So here what we have to consider in the second step, we have to consider the CFSE, that is crystal field stabilization energy for these two ligands. So this fluorine is weak field ligand and this Cn is strong field ligand. You can memorize in this manner. First halogens. Halogens are having lowest CFSE, then the oxygen, then the nitrogen, and then carbon. So carbon donor atoms, these are the donor atoms. So here this carbon donor atom is having maximum crystal field stabilization energy. About this crystal field stabilization energy, I will discuss it in detail in the coordination compound videos, so which is proposed next to this series. Now coming to the ligands which we are having in these complexes. So order of CFSE is iron is having lesser crystal field stabilization energy as compared to the Cn. how does these ligands affect the filling of electrons in the d orbital. This is the step 2 to decide whether it is weak field ligand and or this is strong field ligand, and on the basis of this weak or strong field ligand we are filling the electrons. So the filling of electrons will be takes place like this. So here in the gaseous state of this metal ion, all 5d orbitals are degenerate, which is not the case when ligand is attached to the metal atom. So here these 5 degenerated orbitals will split into two sets of orbitals. This one set of orbital is called T2g orbital, and these two orbitals are represented as EG orbitals. So here we are having dxy, dyz, dzx, and here we are having dz square and dx square minus y square. First I will show you the crystal field stabilization energy for these two ligands. So for weak field ligand, this delta 0 is smaller as compared to the EFSC for the strong field ligands. And here pairing energy is greater than the crystal field stabilization energy. It means if we are going to pair these electrons with each other, that will take more energy as compared to the unpaired electrons, right? So in weak field ligand, we are having unpaired filling of electrons in such a manner that one electron is filled in the T2g set, then we are moving to the EG set. Whereas for strong field ligand, pairing energy is lesser as compared to the crystal field stabilization energy. So here first we are going to fill electron number 1 in the first orbital, second in the second, and third in the third orbital. Now coming to the fourth will again go to the first one and then second one. So this is the fifth electron. So this is how 5 electrons are filled in the strong field ligand, and this is how electrons are filled in the d orbitals in the weak field ligand. So on that basis, we are going to fill in the electrons in the d orbital in such a manner. In the weak field, 1 in each, and in the strong field, right, you can see over here. So T2g set is filled, EG set is empty, because more energy is required to fill these EG orbitals as compared to the pairing of electrons. So in this manner, once we come to know in the step 3 how to fill the electrons in the d orbitals, then the next step, that is step number 4, we have to calculate the orbital angular momentum for this d orbital, right? So here electrons are filled in this manner, so the summation of ml is this much, right? So summation of ml is +2 +1 0 -1 -2, and all are cancelled out with each other, so we ultimately get 0 value, and corresponding to this 0 we are having S term for this type of configuration. Now the step number 5, we have to calculate the spin multiplicity. So spin is 1/2 1/2 1/2 1/2 1/2 means 5/2. So here capital S is equal to 5/2. And the spin multiplicity is 2s plus 1, which is equal to 6. So the term symbol for this FEF63 minus is 6s. So instead of doing this, if you are in hurry, then you can calculate simply by this. Step number 5, n plus 1. So n is number of unpaired electrons. So 5 unpaired electrons, 5 plus 1, 6s. So you can directly check 6s from here, right? Rather doing this exercise. Now coming to the next one, next example, FeCN6 minus. The filling of electron in this manner. Now coming to calculate total orbital angular momentum. So how we are going to calculate total orbital angular momentum? So +2 for this electron, +2 for this electron, +1 for this electron, +1 for this electron, and 0 for this electron. So +2 +1 0, +2 +1, and on adding all these we are getting 6, and corresponding to this 6 we are having I term symbol, right? Now calculating how many unpaired electrons are there? 1 electron. So 2I will be the term symbol, but in between we have to calculate the spin. So S is equal to 1 by 2. Opposite spins will cancel out each other. Now coming to the spin multiplicity. So spin multiplicity is 2s plus 1 is equal to 2 into 1 by 2 s plus 1. This gives us 2. So as I said you earlier, by this rule you can easily calculate from here only, right? So this is the answer. Now one more point can be asked, calculate their spin only magnetic moments also. So here the spin only magnetic moment is under root n plus 2 bond magnetron, right? So n is the number of unpaired electrons. Once you come to know how many unpaired electrons are there, so in case of FeF6 we are having 5 unpaired electrons. So for these 5 unpaired electrons we are having the spin only magnetic moment as 5.92, means the number of unpaired electrons, that 5 point something, right? Here how many unpaired electrons are there? So 1 electron is there. So the spin magnetic moment for this 1 electron is 1 point something, that is the value is 1.73. So I remember all these values up to 5. For 1 it is 1.73, for 2 it is 2.83, for 3 it is 3.87, for 4 it is 4.90, and for 5 electrons it is 5.92. So I memorize all such values. So here the next question, as I suggest you, the oxidation state, how does it affects? So here step number 1, calculate the oxidation state. So how we are going to calculate the oxidation state? Iron X plus subscript 6 into, if your molecule is neutral then it is 0, equal to plus 2 is the charge. So here plus 2. 6 into 0 will gives me 0 and X is equal to 2. This can be done by simple trick. So here you are having iron, water molecule. So water molecules are neutral in nature, so no contribution towards the charge. So iron will have the same oxidation state as written on the complex ion. So iron is in 2 plus oxidation state. The next step is to write down its electronic configuration. So as I told you earlier, 26, 6 will go to the D6, 4s2 D6, right? Now for second oxidation state of iron, it can be written like this, means we have to remove 2 electrons. So the 2 electrons will be removed from this 4s orbital. Now the third step is to check whether it is strong field ligand or it is weak field ligand. So water, as I told you earlier, oxygen donor ligands are weak field ligands, so it's a weak field ligand, or we can say moderate field ligands. Now writing the electronic configuration in such a manner. So here pairing will not occur and we are having 4 unpaired electrons. So if we are having 4 unpaired electrons, so the next step, step number 4, we have to calculate the total orbital angular momentum. So on calculating this, what we will get? We will get for 5 unpaired electron we are having 0. The only electron is this plus 2. So the L is plus 2, right? This is a trick actually. If you are having all the orbitals half filled, so cancel out them, because we will get ultimately 0, and the next electron will gives the value. So it is having plus 2 value, right? So corresponding to 2, we are having D term. Now 4 unpaired electrons are there, so it will be 5D answer. But in between, if you want to check, you can check through this, right? So the term symbol is 5D.